All right, as we get started today, going to start with a review exercise. Practice exercise number 58 is where we'll be today. Practice exercise 58. More algebra review, making sure we keep those skills sharp for next year, regardless of which math class you're taking next year. You'll need those algebra skills to be honed a little bit. Practice exercise 58, and you may begin. Whoever finishes first, stand up and keep track of who's next. Let's go and take a look at these together. Quentin was first. Quentin, let's go across the top row. What did you get for X?
16.
Good.
6.
Yep.
5.
Yep.
20.
Good. 16, 6, 5, and 20 are correct. Next row.
9.
Good.
15.
Yep.
9.
Yep.
6.
Good. 9, 15, 9, and 6 on that next row. And then the bottom row for the candy.
Negative 3.
Yep.
20.
Yep.
Negative 2.
Mm-hmm.
1.
Positive 1. Good. Negative 3, 20. Negative 2, and positive 1. All correct. Great job, Quentin. Anyone else get them all right, though not as fast as Quentin? Okay, a couple of you. How many of you just missed 1? Just missed 2? Questions on the 1 or 1s we missed? Going once. Going twice. Go on, pass those forward if you would, please. Go and pass those forward, and take out your notebooks. Pass them forward, take out your notebooks. Turn to the Theorems Corollaries section of your notebooks. Theorems Corollaries section of your notebooks. We're going to move on from arcs and angles. We can't forget arcs and angles, and we are going to continue to use the ideas that we worked on with arcs and angles. But we're going to move on from some of the numerical exercises and bounce back to proofs for just a little while. Theorem 46 in your notebooks. says this, arcs of a circle intercepted between parallel lines, not by parallel lines, but between parallel lines, there's a difference. Arcs of a circle intercepted between parallel lines are equal. Arcs of a circle intercepted between parallel lines are equal. Once you have that down, and turn to the proofs of theorem's corollary section. Turn to the proofs of theorem's corollary section at the top of a new sheet of paper. Theorem 46. Parallel lines cut off equal arcs between. Parallel lines cut off equal arcs between. It's about as short as I could try to make it.
Could you just Theorem 46?
Pretty much, yeah, I mean, it's basically recopied it. Go and draw a circle on your paper or your close approximation to a circle. And if you would draw a couple of lines that go through the circle, but here's my recommendation. Try to draw them so they don't appear to be the same distance from the center, just so we don't assume something that's not true. So maybe draw one that's really up high toward the circle, toward the top, and then maybe one that's maybe a little bit closer toward the center. Let's call the lines M and N. Let's call these lines M and N. Let's call the points of intersection A and B, C and D, and we can call the circle O. Let's call the circle O. We are given M parallel to N, M intersects circle O at A and B, N intersects circle O at C and D. Move this out of the way so everybody can see what we're doing here. M parallel to N, M intersects circle O at A and B, N intersects circle O at C and D. We're going to try to prove that the arcs intercepted between them. Now, for clarity, line M cuts off or intercepts arc AB. Line N intercepts arc CD. These arcs are not the arcs we're trying to prove are equal. We're trying to prove that the arcs intercepted between them are equal. So we're trying to prove that arc AC is equal to arc BD. Does everyone see what we're trying to prove? Does everyone see that they kind of look equal to each other, right? I mean, and again, the nice thing about circles is, even though we don't trust our eyes, with a lot of the circle proofs, things often look to be the way they are, and things are often the way that they appear. So that's going to make it a little bit easier for us. All right, once you get this down, 2 columns, statements, reasons. Two columns, statements, reasons. Write down your first statement and your first reason. By the way, for the record, since posterity may see this, I did not lose all fashion sense today. It's tacky day here at Grace Christian School, so hence the weird everything. Just in case, yeah, mainly the weird tie is what you're going to see on the video, but yeah, anyway.
I like that.
So, what?
That's the kind of tie I would wear, though.
Hopefully you wouldn't wear it quite this way. I like the tie, it just doesn't go with the green shirt, and the back of the tie should never be red. Yeah, red shirt, that's the only thing worse, frankly. Yeah. But red would have actually gone with black pants, and the green didn't go as well. Anyway, all right, but I digress. All right, so we want to prove that 2 arcs are equal to each other. Well, We want to get two arcs equal. Oftentimes to get arcs equal, class, we try to get central angles equal, or perhaps chords equal. So that's one option here. I suppose we could try to get a central angle here. Don't do this on your paper. And a central angle here. Might be a bit challenging. Here's another thought, though. We do have parallel lines. And usually when we think parallel lines, class, we think
Equal, or angles.
equal angles, right? But we only would get equal angles if we had a
Well, or trapezoid.
transversal, right? We would need a transversal to make that happen, right? I think we're thinking the right words: triangle, trapezoid. We know it's a TR. We're transversal, right?
Draw one.
So let's go ahead and do that instead of trying to get central angles, and we'll actually use a different kind of angle. Now that we've spent time talking about arcs and angles, we have a few more options available to us. I'm going to start by drawing this transversal from B down to C. From B down to C. So number 2, draw BC. Now, reason, of course, class.
2 points in a triangle, or in a circle.
Well, you just say 2 points determine a straight line. Because anytime you have 2 points, no matter where they are, it always determines just a single straight line. So 2 points determine a straight line. Now, the nice thing is, when I draw this line, like we said, it's a transversal, right? So if I call this angle 1, this angle 2, it gives us a couple of angles. Specifically, 1 and 2 are what kind of angles, class?
Corresponding. Alternate.
Alternate interior angles, because they are alternate interior angles. They're on alternate sides of the transversal, they're between the respective lines. And we know that alternate interior angles of parallel lines are equal. So number 3, we could say that angle 1 equals angle 2, because alternate interior angles of parallel lines are equal. Now, 1 is not a central angle. 2 is not a central angle. 1 and 2, class, are inscribed angles. What do I know about an inscribed angle, Genesis? It's equal to half its arc, which means, Genesis, that angle 1 must equal half of arc BD. Similarly, Genesis, we could say that angle 2, because, just write out our thought is because an
inscribed angle equals half its arc.
If you want to sound really cool, an inscribed angle equals half its intercepted arc, but I'm lazy. So an inscribed angle equals half its arc. And we know that these are equal to each other. So how might I tie statement 3 and statement 4 together, Jamie?
You could say that you could do like substitution. 1/2 of BD equals 1/2 of AC.
There we go. Do we all see the substitution that Jamie did there? Right? And again, as she already said, the reason simply substitution. All right? Now that's really close to what I want, right? I wanted AC and BD equal. Right now I have half of BD equaling half of AC. Well, from algebra, if I have fractions in my equation, how do I get rid of them? Multiply the LCD. So what would I have to multiply both sides by, class? 2. What do we call multiplying something by 2? We call it doubling it, correct? So if I multiply both sides by 2, the 1/2s drop out, and I'm left with exactly what I wanted, because what did I do to equal quantities? I doubled them. And we know that doubles of equals are equal.
Oh, it's halves of equals are equal.
That's also true. The division axiom says that halves of equals are equals. The multiplication axiom says that doubles of equals are equals.
Are they different things?
Yeah, they're 2 different axioms. Doubles of equals are equal.
Okay.
So therefore, BD equals AC, and boom, we've got our proof. Now, technically, class, this is only one of 3 ways that this proof would have to be shown. I'm going to show the other 2, but we're not going to put them in our textbooks. The other thought would be this. Well, what if, instead of 2 parallel secants, what if you had a secant and a parallel tangent? Well, much the same idea. You could draw a line to the point of tangency, call this angle 1, call this angle 2. We know that angle 1 and angle 2 are equal. Angle 1 is an inscribed angle. It equals half its arc. Angle 2 is not an inscribed angle. So we would take one more statement. You'd have to do this separately. It's an angle formed by a chord and tangent. It also equals half its arc, which means these halves of these arcs are equal, which means when you double them, the arcs are equal. Same exact proof, plus one step, because you can't put these together. One would be inscribed angle, one would be chord and tangent, but it would be a 7-step proof. Okay? The other way you could prove it would be to have two parallel tangents. Now, one thought would be, well, if you were to construct the perpendicular to a tangent, we know the perpendicular to any tangent passes through the center of the circle. And we also know that any line perpendicular to one of two parallel lines is perpendicular to the other also. And we know then that a tangent is perpendicular to triangle at the point of tangency. So these are both perpendicular, and therefore this is a diameter, and therefore these are both semicircles. That's one approach, I suppose, to the proof. The technical wording of it can be a little dicey. The alternative then is draw an auxiliary secant. Well, we already proved that between a tangent and a secant, these two arcs are equal. And between a tangent and a secant, these two arcs are equal. If equals are added equals, the sums are equal. And now we don't have to worry about the picky perpendicular and diameter and all that, which can be a little bit dicey. So again, pretty straightforward there by adding the secant once you've proven this here. So it'd kind of be a progressive proof, yes.
Would that be slower? Like a lot slower?
I don't know that it would be. I think
it'd be
because you don't have as many nitpicky details, right? Sometimes proofs can get bogged down. Well, technically we do have to state this, don't we? Oh yeah. Well, and technically, you got to state this too. Oh, yeah. And there's all those oh, yeahs, and next thing you know, you've added 5 statements. I almost feel like adding the auxiliary line would actually make it a quicker, more direct proof.
Compared to what we did.
Well, these would be 3 separate proofs, except that this one would have to follow this one. So, no, this proof would end up being longer, but it would be contingent upon having proven that chord or secant and tangent parallel intercept equal arcs. So basically, what we need to know, you got parallel lines, arcs between them have to be equal. Class notes section of your notebook now. Based on that truth then, y'all mentioned the word trapezoid earlier. Think about it for a minute. What do we know about a trapezoid, class? 2 parallel sides, right? Well, if you have 2 parallel sides, if you were to inscribe a trapezoid, 2 parallel sides, what has to be true about the arcs in between those parallel sides? They have to be equal. And if you have equal arcs, that means you're also going to have equal chords. So picture this. You take any 2 parallel lines, and you draw 2 lines that are not parallel. You've drawn an inscribed trapezoid, right? But because these arcs have to be equal, these chords have to be equal. Therefore, any trapezoid inscribed in a circle must be isosceles. Write that down. Any trapezoid inscribed in a circle must be isosceles. Any trapezoid inscribed in a circle must be isosceles. Any trapezoid inscribed in a circle must be isosceles. I just talked through the proof, so we won't do the proof. Another thought for you. Let's suppose you wanted to put a parallelogram inside a circle. Well, we know for a parallelogram, these 2 lines parallel, those 2 lines parallel. But are you picturing how hard it's going to be to slant those lines? Yeah, I mean, if you have these 2 sides parallel and equal, so equal arcs, and you have 2 more sides parallel and equal, so you have equal arcs, then that means if you were to go from one corner to the next, you'd have these 2 arcs. Then if you go from one corner to the next, you'd have these 2 arcs. The sum of these must, class, equal the sum of the other. Therefore, these 2 pieces are equal, and they consist of the whole thing. The whole thing is comprised of 2 equal parts. We refer to these equal parts as halves, and a half of a circle is called a semicircle. And any angle inscribed in a semicircle is a right angle. Therefore, write this in your class notes, any parallelogram inscribed in a circle is a rectangle. Any parallelogram inscribed in a circle must be a rectangle. You cannot inscribe a parallelogram that is not a rectangle, just as you cannot inscribe any trapezoid that is not a rectangle. Trapezoid, you cannot inscribe any trapezoid that is not isosceles. So some interesting facts there. Questions on those class notes items. Commit those to memory, tuck those thoughts aside, but as I said, we already kind of talked through the proofs there. Go ahead and take out just some blank paper to work some proofs on here. We'll do just a couple more proofs this hour, get us back in the proof mindset. But again, as we saw with Theorem 46, we can use inscribed angles. We were limited to only central angles before, weren't we? But now we can use central angles, inscribed angles. We could even, heaven forbid, chord and tangent, two secants and tangent, or things like that. All those arcs and angles, we can use them in proofs as well, if needed. Page 156 in your textbooks as well. Sorry, so paper, pencil, and your textbook as well. Page 156. And at the bottom of the page, by the way, you do see kind of a summary section. You wanted a dog ear or maybe sticky note that page for yourself. This is a good refresher page. That said, pretty much everything in here is so intuitive. I don't know that these are going to be as easy to forget. So I don't want to spend a lot of time here. Do note, though, in bold at the top of the page, all of these things are true only in the same circle or congruent circles, right? So we know nothing about anything if they're not in the same circle or congruent circles, just for the record. All right, bottom of the page, page 156, number 1. Chris, go and read it for us nice and loud.
Prove that if from either end of a diameter, chords are drawn making equal angles with the diameter, meaning chords are equal.
Read it for us again, if you would, Audrey.
Prove that if from either end of the diameter, chords are drawn making equal angles with the diameter, then chords are equal.
Quentin, read it for us. Pause at strategic points as you read to add emphasis and to add some expression. Read it for us, Quentin.
Prove that if either end of a diameter chords are drawn making equal angles with the diameter, then the chords are equal.
All right, at your seats, I want you to try to draw the picture. There are two different ways you could draw this. You draw the picture. Don't do anything else but the picture. Don't even label the picture. And we'll go over it and make sure we know how to set this up. Prove that if from either end of a diameter, chords are drawn making equal angles with the diameter, then the chords are equal. See if you can figure out the picture. Two different ways you could do it.
Can we use more than one chord?
Prove that if from either end of a diameter, chords, plural, are drawn, making equal angles, plural, with the diameter, then the chords, plural, you better have two chords.
Like, can we make a triangle?
I suppose you could. Though, you will assume things, that you will prove, your proof will actually be easier, but you'll only prove, probably, you'll only prove that it's true if they meet up. So let's assume that chords don't actually meet on the circle. I think here's what Chris is asking. We have a circle. Hopefully you all drew a circle, right? Yeah. And you all drew a diameter in your circle. Okay, it didn't have to be horizontal. I chose to. I think what you're saying, Chris, is if you were to draw chords that make equal angles that meet up here at the top,
I did
right?
on both sides. Yeah, I guess I didn't have to do it on both sides, but I did.
Right. It's just two chords are drawn, so they make equal angles with the diameter. Now the problem is if you make them meet, you're gonna probably do the proof in such a way that it only works if they do. What we want to do is use a proof that works whether they actually meet up or not. So I would recommend one of two ways drawing the picture. Okay, so edit your picture to match one of these two ways if it's not already there. Method number one was to kind of take what Chris did, but instead of having the equal angles make them hit up here, make the equal angles such that they don't actually meet. Does that make sense? That's one way. Now, there's another way you could have drawn it. You didn't even have to draw them so they both went up. You could have had one going up and one going down at the same angle. This would also work. Okay, so either picture will suffice. How many have one of these two pictures already? All right, so several of you did. How many had them both going up at equal angles? How many had them going opposite directions, one up, one down? A couple of you did. The proof will work the same. I'm actually going to use both pictures, though. Question?
So on the one I had drawn originally with the triangle, if we had drawn, say, a line from the vertex down to the base, wouldn't that have made central angles?
It would have.
And that would have, we then four could have gotten equal coordinates.
Well, but would you have drawn one line or would you have drawn two?
What do you mean?
You would have drawn one line.
Yeah.
Does that necessarily, it gets a little challenging. So it would be best to have them not meet just so we don't assume something. Because again, you're going to say, well, we've got this triangle, so therefore equal, oh, careful. We don't know that it's necessarily going to form a triangle. Let's call the center of our circle O, for sake of being consistent with what we do all the time and boring. All right, let's call the center of the circle O. Let's call our diameter AB, regardless of, again, how we've got the picture set up. And let's call the chord coming up from A, let's call it AX. And let's call the chord coming from B, BY. So again, there's two different ways in which this picture could look. You could have this one or this one. You certainly don't need both. I'm going to show both. All right, gentlemen, work as fast as you can for 20 minutes, so that way, that is tacky, by the way. Just at the door. Work quickly. You only got 20 minutes for an assignment that probably you plan to take more like a half an hour. So to avoid having homework tonight, work as fast as you can. And here's what we're given. We're given, regardless of which way we drew it, circle O with diameter AB and chords AX and BY. Now again, here's where your picture wouldn't have worked, Chris, because we would have had the same ending letter. Well, you couldn't have drawn it this way. Again, it only works if, so having the two separate points is needful because now it doesn't matter how you draw it. Chords AX and BY such that angle A equals angle B. Such that angle A equals angle B. So we have chords drawn at the ends of a diameter, making equal angles with the diameter. We want to prove that if two chords are drawn, making equal angles with the diameter at either end of the diameter, that the chords class are equal. So I want to prove that AX equals BY. I want to prove that AX equals BY. And again, the nice thing about circles is it kind of looks like they would be equal, right? So not that we trust our eyes and say, well, they look equal, so they are, but you know, it's not like we're trying to prove something that doesn't even appear to be so. Two statements, or two column statements, reasons. Circle O with diameter AB and chords AX and BY such that angle A equals angle B. Economics guys are like, oh, I miss this so much. Question, Chris?
Yeah. So somewhere in the notebook we have something that says like any point from any point on a diameter it's equidistant. Is that in a triangle? Like if it's equidistant to the opposite line?
I'm not quite sure what you're talking about.
From any point on a diameter, it's equidistant.
What's
to the
equidistant?
endpoint.
You say it.
Like a line.
From any point on a diameter, a line is equidistant?
A line is equidistant from that point to the endpoints of the opposite.
Oh no, you're saying in any point
bisector.
perpendicular. In a perpendicular bisector of a line, any point in the perpendicular bisector of a line is equidistant from the ends of the line. Not a diameter, perpendicular bisector is what you're thinking. Okay. Hey, but at least we cleared up what you were thinking. Yes, sir.
Couldn't you draw X, Y, and make a trapezoid? Trapezoid.
Okay, so here's Ethan's thought. It's a great thought. All right, if we were to draw X, Y to make a trapezoid, we had just stated, and not necessarily written out the proof, but talked through the proof that in a trapezoid, it has to be, if we draw a trapezoid, it's got to be isosceles, so therefore, legs are equal, boom, we're done. Anyone see the problem with that?
We would get the wrong thing. That's not what we want.
It is what we want. We do want AX and BY equal.
But
Now,
it wouldn't be equal. It'd be AB and XY being equal.
ooh, no, certainly not. The legs of an isosceles trapezoid are equal, not the bases. Would this be a trapezoid if you drew XY class?
No.
That's the problem,
Why not?
right? To know that it's a trapezoid, these two lines would have to be parallel. Do I know that they would be parallel? But I mean, the thought was good. The thought was there. It's just yeah. But that's where it falls apart. Is well, how do you know it's a trapezoid? Oh.
Why don't we just
Yeah.
say clang?
All right. So clang. All right.
AO equals BO.
We could do AO equals BO. Actually, I'm going to need to wait on that one. Actually, let's wait just a little on that for one key reason.
Angle A equals angle B.
Right. It's in the given.
Yeah. So, no, it's not in the triangle.
Yeah. No. Don't you, that triangles make life so much
Draw a
easier.
triangle.
You can draw it.
Let's just draw a triangle. Draw.
Right, and this is why I wanted to hold off. Draw XO and YO, right? Drawing radii will often help you in a proof anyway, right? But especially when they give you triangles, and especially when you can say that all radii are equal, I mean, that's eventually got to help somehow. Now, I do want to point something out. You cannot assume that XOY is a straight line, okay? XO and YO are not necessarily in a straight line with each other. So especially those of you with this picture, avoid thinking, oh, that's a diameter. No, it isn't necessarily a diameter, okay? And so we don't necessarily have vertical angles, just so we're clear. All right, so number 2, draw XO and YO. And Ethan, your suggestion, reason?
I have 2 points determined as a straight line.
So does XO and YO become a diameter? Do they become radii?
Well, are they drawn from O to any point on the circle?
Well, yeah.
So since XO and YO are radii, now, Chris, is a good time to go ahead and say that.
Well, now everything would equal each other. AX would equal XO.
Whoa, AX?
Yeah, because
Is AX a radius?
Yeah.
AX is a radius?
Oh, it's not any point in the center. No.
Right. But you
Okay.
said AO and BO. I wanted to hold off because I also want to get not only are AO and BO equal, but also XO and YO. So XO equals YO equals AO equals BO. And Kendall, reason?
All radii in the circle are equal.
I'm going to stay with you, Kendall. Now, Kendall, what becomes my thought in trying to get these 2 lines equal or these 2 lines equal? Congruent triangles, right? Do you see the congruent triangles? Now, what do I already have that can help me toward getting congruent triangles, Kendall? I've already got a couple of sides equal, and I've got a couple of angles equal. So, Kendall,
Triangles are congruent.
by...
Angle side? No.
Ooh, you're right. Yeah, because the angles would have to be these 2 angles, wouldn't they? It's actually side angle. And is side angle approved? No. Okay. But we do have sides and angles, right? We just happen to need something more than what we have. We can't get another side, agreed? Because we'd already have the proof at that point, at least as far as congruent triangles are concerned. Maybe another angle? Thoughts? Chris, you've helped me a lot already. Genesis, you've been quiet here. Thoughts on some angles that might maybe possibly we could get equal? Oh, I forgot to mark this. Angle X and angle Y. Now, I don't know right now that they're equal, but Genesis, if I were to look at just triangle AOX, thoughts on just this triangle? 2 equal sides, so therefore, if you have equal sides, it doesn't necessarily mean the third side's equal, but if you have 2 equal sides, it means you also must have 2 equal angles. Specifically the opposite angles, right? So what 2 angles must be equal? I'm going to call these angles 1, 2, and 3. 1, 2, 3, and 4. What angles must be equal, Genesis? Be careful now, because these 2 sides are equal. What are their opposite angles?
1
No, 1 is across from AX. What's across from OX? What's across in this triangle? What's across from OX? A. What's across from AO? X. So since these sides are equal, these two angles must be equal. Number 4, we can state that angle A must equal angle X. And the same would be true over here. Two equal sides equal angles A and X, regardless of how your picture is set up. Because, how might we word our reason, Genesis?
Angles opposite equal sides triangle.
Good, but not only is that going to be true over here with angle A and angle X, Chris, but
angle B and angle Y.
right, because BO and OY are equal, so angle B across from OY and angle Y across from OB have to also be equal.
And if A equals B, then you can substitute.
Good, and going back to the given, since we knew that A and B were equal, we can do a substitution, Jamie, that says
That, what is it? That A, right? Oh, angle X equals angle Y.
good. Substitute X in for A and Y in for B. X equals Y by, you said it was
Substitution.
substitution. And so now I have side angle angle or side angle angle, and that is a way of proving triangles congruent, right, Kendall? So number 6, Kendall, back to you. We can say that
Triangle AOX is triangle AOY.
and reason
Side
side angle angle. Now, why did we want congruent triangles again, Audrey? Because we wanted our two chords equal AX and BY, and they will be by CBCT. So once again, back to the triangles, right? Questions on this proof? Questions on this proof? All right, let's take a look at the next page. Top of the page, number 5. Top of the next page, number 5, page 157. And Jamie, go ahead and read number 5 for us, nice and loud.
Prove that if two secants to a circle from an external point are equal, then the intercepted chords are equal.
All right, read it for us again if you would, Ethan, nice and loud.
Prove that if two secants to a circle from an external point are equal, then the intercepted chords are equal.
All right, and one more time, Genesis, nice and loud.
Prove that if two secants to a circle from an external point are equal, the intercepted chords are equal.
All right, set up your picture. It shouldn't be too hard this time. Prove that if two secants to a circle from an external point are equal, then the intercepted chords are equal. Hopefully, you have a picture something like this. How many have two secant lines coming from the same point, and the lines are approximately equal to each other? Again, we don't trust our eyes anyway, but approximately equal. All right, questions on how we got this picture? All right, if you didn't have this picture, go ahead and get it down. Let's call the circle Q. We'll mix it up a little bit here. Let's call this point out here P. And let's call the first 2 points of intersection M and N. And let's call the latter points of intersection S and T. Just use some letters we don't use as often. And we are given circle Q with secant PS equal to secant PT. So we have two equal secants from the same point. By the way, will two secants from an external point always be equal? No, there's a whole lot more secants I could draw that would be bigger. By the way, think about it for a minute. What would make how would I make sure I get a bigger secant from P? Thoughts?
What do you mean?
For instance, if I wanted a smaller secant or a bigger secant, it all depends on how I draw the line, but it's still going to be determined by the second point of intersection, right? Maybe it's a hard...
The closer to the center, the
Bingo! The closer I get my secant to the center, the bigger that secant's going to be, right? Oh, okay, so if they look approximately, now we haven't proven this, but if they're approximately equidistant from the center, then the secants are equal. So that's kind of how to draw the circles, try to make them look about the same distance away. But we've got two equal secants. But we want to prove, though, what again, Jamie?
That the chords are equal?
Now listen, we cannot prove that these, the chords? Not the arcs, the chords?
The intersected chord?
Oh, I'm sorry, okay, I was picturing arcs. All right, sorry, forget what I was about to say. The intercepted chords are equal. Now what chords are intercepted? Well, a secant, remember, consists of part chord, part piece on the outside. We want to prove that if the secants themselves are equal, which is then the chord portions of them must be equal, which would mean that they would be equidistant. So to prove that SM equals TN. Sorry, my brain was ready for arcs, that chords. Prove that chords are equal. I need to pay attention to what you're reading. All right, prove that SM equals TN. Now again, we have not proven that if secants are equidistant from the center that they're equal. If we could, then we just say, oh, the secants are equidistant because they're equal, and if they're equal distant, then the chords are equal. So I mean, that'd be super easy. But intuitively, we kind of figured that out. Once you got this down, two columns, statements, reasons. First statement, first reason. And I'm going to skip the word secant and copy it down to say circle Q with PS equal to PT for sake of ease, for the sake of time. I have two big lines that are equal. I want to prove the little pieces are equal. Thoughts?
Why don't we draw QS and QT?
QS and QT.
Or QN and QM.
QM and
They
QN.
would both form angles.
Alright, so you're saying draw this and that, draw this and that.
Or you could just draw QT and QS.
Could you draw
I think it would work the
perpendicular?
same, honestly.
I could draw the perpendicular. I think you're going to wind up having a harder time with perpendicular. Now, Chris's thought is interesting because if you can get the triangles congruent, Chris,
And you have equal.
then equal chords, right? And I already know I've got two sides equal here, two sides equal here. The hard part would be getting either this or that or this or that or this. Getting angles equal is going to be hard. But,
You would already
wait a
have
second.
QS and QT.
equal, what, I'm sorry?
Wouldn't you already have QS and QT?
Well, yeah, they say equal lines.
So that would give you side, side.
Side, side, but there's got to be that other angle somewhere, right? And I'm not sure how we'd come up with the angle
wait,
this way.
Wait, angles opposite equal sides in a triangle are equal.
Right, that would mean that these two angles were equal to each other and these two, but you could have equal lines like this and equal angles like this, but the angles here not necessarily be equal. Does that make sense? So, but I do have what Chris said a moment ago. I've got equal lines. If only I could make a triangle with these two
TS.
equal lines.
Draw TS.
Let's draw TS. Because then I know for sure I can get a couple of angles equal. What angles would have to be equal, Ethan, if I drew ST or TS, which was your suggestion?
Angle S and angle T.
Right, the whole angle at S, that angle at T. So 2 points determined.
Straight line.
Paste it one. And that'll give us angle T and angle S equal to each other. Because
Okay.
Yeah.
It
it was your idea.
opposite angle.
How about angles opposite?
Angles opposite equal sides in triangle equal.
There we go. Angles opposite equal sides in a triangle are equal. The only problem is that got us a couple of equal angles, Ethan.
What about SN and TN? Would that do anything?
SM and
No, I
T.
mean SN and TN.
Oh, okay, now this is an interesting thought. If we were to go with these chords here, focus with me now. Do we see that that gives me a triangle, STN? Do we see it? And a triangle, TMS. These are sides of those triangles. So again, I'm looking at this triangle and this triangle. Now I already know that they've got two angles equal. I would also have, obviously, a set of sides equal, Chris. Which side, two sides are equal?
I'm having.
Anyone?
SP.
ST and ST, right? I mean,
Yeah,
it's shared by,
yeah.
it's by itself. So let's unoverlap it. I think that's what you're trying to imply to me, right, Chris?
Yeah, I was having trouble visualizing.
Yeah, we got STM, where we already have this angle, this side, and then we've got the triangle T and S. Stay with me. Seniors, you're dismissed. With this angle and this side. Well, let's go and get this down. Let's get down that ST equals TS. We're actually going to reverse the order because of class identity. Oh, we can't say that yet. What TS are we talking about? We haven't. Oh yeah, never mind. We drew it. Yeah, sorry. So we drew the line, and then Chris suggested drawing SN and MT. Let's do that. Actually, let's put that up here in number 2. Draw TS, MT, and SN. Now we don't have to make another statement because I'm late. All right, draw TS. We already did that. Then MT and SN. You realize if I could get this angle at T, I'm going to call it angle 1. Which is right here. If I could get that equal, and then this angle here, which would be this right here, then that would give me angle side angle.
If you can get 1 and 2 equal? Is that what you said? If you can get 1 and 2?
Yeah, if I could get them equal at an angle side angle,
Well, we already said
or
that T.
if I could get this angle here 3 equal to this angle 4, then I'd have side angle angle.
Well, we already said that angle S equals angle T.
Well, the whole angle S up here equals the whole angle T here. But 1 and 2, 1 is a piece of T and 2 is a piece of S.
And we
Angle
don't know.
3 and angle 4 are both opposite TS.
Good. Do you see that 3 and 4 are what kind of angles? Think of the picture, the whole circle. Picture what we were doing yesterday with arcs and angles. What kind of angle is 3?
Inverse. No.
Class?
Inscribed.
It's an inscribed angle. And we know that an inscribed angle, class, equals half its arc. So angle 3, Quentin, equals half of arc TS. What about angle 4, Quentin? What is this angle? What kind of angle is this? And it also then equals half its arc, which is half of arc TS, because, as you just said a moment ago, and since 3 and 4, class, are both equal to half of TS,
They're equal.
they're equal to each other. Ah. So then, forget angle 1 and 2 then, I don't need those. What do I have, class?
Side angle side. Or side angle.
Side angle angle, my triangles are congruent. Oh, sorry. Number 6, substitution. I didn't get my reason down. And then number 7, we can say the triangles are congruent. We can say triangle TSM is congruent to STN by side angle angle. If the triangles are congruent, then sure enough, the chord portions, TN and SM, must be equal by.
CPCT.
Very good. I left a dramatic flair there, Ethan. CPCT. Homework for this evening is to do number 4 at the bottom of page 156. Page 156. Number 4. Do you see how we can use inscribed angles? Good call, Quentin. to help get triangles congruent, get things equal, things of that nature. Questions? All right, chart is dismissed, and I'll mosey down and tell Pastor how we'll be late again.
I know.